down. Now, you're the only one of 5 to show up for differential equations yesterday, and so far the only one of 3 to show up for linear algebra today. So let's hold off until at least one other person shows up, and then I will make the announcements about how we're going to wrap up the term in this as well as the other classes also, because you've already heard, I think that you heard it for Cal 3 yesterday, and I hope I said it for differential equations yesterday. But well, remind me to do several things when more people get here. Okay. All right, we're in chapter 4, which is vector spaces, and we're in section 4.3, which is subspaces of vector spaces. And we got started on this last time, yesterday, the Thursday before Thanksgiving. Okay, so it's been a couple of weeks now. Okay, or not quite. We're on page 169, and it's the second paragraph, the one that starts, a subspace of a vector space is also a vector space. Now that opens up a lot of possibilities here. It means there's nothing new that you have to do. You just have to prove, number one, it's a subset, and that if it's a vector space, it becomes a subspace. Okay? In fact, the simplest subspace of a vector space is one containing only the zero vector. Okay? Because if you think about that, the zero vector added to itself, everything you do with the zero vector is fine. You've got to have a zero vector, period, so you got it. And that subspace is also called the zero subspace. Okay? So, I guess I ought to write it. It just seems like such a mindless concept, but I guess I ought to write it for you just so you'll see how they note it. So remember, W stands for a subset of a vector space. Okay? Now, if this W consists only of one element, it's a set, so you use set notations here, and if it only has the one element, the zero vector, okay, then that is also a subspace of whatever vector space you came from. It is a vector space itself. That's the simplest vector space and subspace you can ever have. It's called the zero subspace. Now, another subspace of V is V itself. Okay? V obviously is a space because it's a vector space, and it is a subset of itself. Okay? So it's also a vector space, so it is a subspace. Okay? So that's the smallest, that's the largest. V is a subset of a subspace of itself. Every vector space contains these two trivial subspaces, either simply the zero vector or the entire vector space. And other subspaces other than those two, nothing or everything, is called a proper or a non-trivial subspace. All right, so let's take a look at example 2, which is going to be a subspace of 2 by 2 vectors. So I think I will clear that off the screen just so we'll have everything on here pertaining. Okay, here's W. It's a set. I'm going to write a set notation. All 2 by 2 symmetric matrices. That's what it is. Set of all 2 by 2 symmetric matrices. Now, the question is, show that that W, which is a set, okay, is also a subspace of the vector space M22 that's the set of all 2 by 2 matrices with the standard operations of matrix addition and scalar multiplication. Now, what do we mean by a symmetric matrix? Now, 2 by 2 symmetric matrix is pretty simple to do. It would look something like this. Well, matrix notation. 2 by 2, it could have, let's call it little w 1, 1, little w 1, 2, and then this also has to be little w 1, 2. These two entries have to be the same, and this would be little w 2, 2. These two don't have to be the same. That's what, I probably shouldn't have used W, but I just picked a letter and I happen to pick a pretty poor one, I guess. Okay, so that's what it is. Recall that a square matrix is symmetric when it is equal to its own transpose, and obviously this is. W1, W2 is W1, W2. W1, 2, W11, W12 is equal to W11, W22, 1, 2, and W12, W22 is equal to W12, W22. So this is what it looks like, okay? When it's equal to its own transpose. The set M22 is a vector space. We know that. M22 is a vector space, set of all 2 by 2 matrices. Okay? Now, you only need to show that that W, which is a subset of M22, you know it is, okay, because it's all 2 by 2 matrices that are symmetric, satisfies the conditions of theorem 4.5. Okay? And what that is this one. Let's go back and review that. If U and V are both in W, that's the subspace, then U plus V is in W. Okay? And the second of these, if U is in W, and C is a scalar, then CU is in W. Of that subspace W. So basically you just have to show that if the vector addition works and if scalar multiplication works, then, and they're contained within it, then you're in. All right. Now, let's assume, and I really regret my lettering now, they're using A1 and A2. Okay, I just heard something. I don't know what that meant. It was a beep. It's still just the two of us there, aren't there? Yep. Boy, they're leaving you hanging by yourself, aren't they? Okay. Did yesterday and doing it today. I'm hoping those sounds I'm hearing isn't people trying to get in and can't. I don't know why they couldn't, but I checked yesterday too. I never saw them. Okay. Now they start with by observing that W is non-empty. Well, of course it's non-empty. It contains 2 by 2 symmetric matrices, so that doesn't think. So W is closed under addition. Well, let's see if that's true. What we're going to do is assume that A and B are both in W. I mean, A1 and A2 are in W. Okay? A1 and A2 are both in your subspace W. So obviously it's not empty. Now, to do this first one, now remember this is acting like vectors, but remember vectors can be any of these things: matrices, functions, polynomials. There's just a bunch of things that can be, and this same thing hold here. So if A1 plus A2, it's also got to be in W. Okay? Now, let's just think on, I wish they hadn't used A's, but they did. What is that? Well, if these are symmetric matrices, then you know that A1 is equal to A1 transpose and A2 is equal to A2 transpose. That's what it means to be a symmetric matrix. A1 is equal to A1 transpose and A2 is equal to A2 transpose. Okay? So, what we have to show is this sum, this thing here, is also in W. Well, for it to be in W, its transpose must be itself, right? Now, this goes back to something, and I can't even remember exactly where it is. It was back in chapter 2 is my memory, but let's see if that's indeed true. When we first brought up the concept of transpose of matrices. Okay. Goodness gracious, it's way back there. I should have just looked it up in the index. That would have been faster than this. Transpose of a matrix, way back in 2.2. And some of the properties are, if you go back to page 57, you'll see that A plus B transpose is the same as, if I can get my pen to show back up, there it is equal to A1 transpose plus A2 transpose. Okay? They used A and B, but that's the same deal here. Okay. Now, we've just seen that A1 and A2 are NW, and the sum of them will be this thing, but A transpose plus A1 transpose plus A2 transpose is then also the transpose of this is the same as A1, and the transpose of that is the same as A2 from up here. So A1 plus A2 transpose is the same as A1 plus A2. So we have just shown that if U and V are in the set, and they are in the subspace, or they are, then their sum is in the subspace. And we knew it was because A1 and A2 were in it, so therefore the sum is in it. So basically we've just proven it. Boy, that was half the book that we've covered so far, more than that before we went back to it. Okay, and that's basically shows that. Now the second part is that I wish I'd left the place because I'm going to need it again. Yeah, I've got it. Okay, the second is that if U is in W and C's any scalar in the world, then Cu is in W. So this says A1 is obviously in W. Okay, C's a scalar. Now is C A1 also in W? That's the question. We don't know that. Okay. Well, the transpose of this is equal to its transpose, A1 transpose, and so if A1 is in that, then A1 transpose is in that. So C A1 transpose would also, because those are the same, these are equal to each other, because these are equal to each other, and that would then mean this is in W as well. So if the A1 is in it, A1 transpose is in it. Okay, I don't know if that satisfies what they do. Similarly, W is closed in scalar multiplication because A1 equals A1 A equal A transpose implies that C A transpose is CA in parentheses transpose is C times A transpose, which is CA. So yeah, it's in it too. These sometimes get so, the very obvious things are the things that are the hardest to prove, because you think, well, that's just so obvious. How do we prove that? But that is the proof, you know, that it is true. So sure enough, and the other way to look at this is, I wish I had used different symbols. Let me use it. For A1, let's use little a. This is going to be difficult. Little a, let's just do little a. And A2 we'll use little b. So this would be little a 1 1, little a 1 2, but because it's symmetric, that would have to be 1 2 here and little a 2 2. Okay. And for A2 we're going to use the b's, B1 1, B1 2, and then because it's symmetric, this has a B1 2 again, and B2 2. That doesn't have to be the same. And if you did adding these two together, A1 1 plus A plus B1 1, A1 2 plus B1 2, A1 2 plus B1 2, that's symmetric. and then, you know, these two doesn't matter. Okay, and if you did C times this one, either one of those, that would be C A 11, C A 12, C A 12, and C A 22. Okay, and that's also symmetric. Okay, because those two are the same. So basically, that's all you had to do. I would have rather done it this way. Actually, the transpose thing does well. The other one just is so obvious you wonder if you really showed it. Okay. Let's move on to example 3. Do you need this left up here any longer? Okay. Let me just make sure nobody else is here. Nope, just the two of us, just like yesterday afternoon. Okay. Example 3. Let W, goodness gracious, it's hard to find my cursor on this thing sometime. There it is. Okay. Let W be the set of singular matrices of order 2 okay, that's it, singular matrices of order 2. Show that W is not a subspace of, I don't know how to do that, not a subspace of M22. So that's all your 2x2 matrices when you're using the standard operations. Okay. Set of all singular matrices of order 2. Now, remember what singular means? Non-invertible. Okay? Okay. Set of all singular matrices of order 2. So they are 2x2 matrices, so they're a subset of thing, and actually this symbol here says not a subset of. I don't have one for not a subspace of, so I think I'll go back and correct that because that's technically not correct. Show that is not a subspace of M22. So that was perhaps easier. Okay. Now, and I drew it in a couple times and it keeps disappearing. Okay. Hold on just a minute. I've got before class I was eating a few almonds just to stave off hunger, and it seems like that last one something got stuck in my throat, so I'm having trouble talking. Okay, now sometimes these things are easy and sometimes they're not. Basically, if you can come up with one reason it's not, okay, then you've done it. It's sort of hard to show everything like we did for when they are, but we need to come up with one that's not. So we need to come up with a singular matrix of order 2. Okay? I would suggest here's 1. 1, 0, 0, 0. That obviously does not have an inverse. Okay, it's not invertible. Okay, because it has a row of zeros at the bottom. Okay, here is another one that is non-singular matrix. 0, 0, 0, 1. Okay, now if you were to add these two together, you get 1, 0, 0, 1, 1. Now, this obviously is a non-singular matrix because it's an identity matrix and it has an inverse itself. Okay, neither one of these are singular matrix. I mean, both of these are singular matrices, and in order for it to be a subspace, when you add two singular matrices together, you must get a singular matrix. This is not singular matrix. So that's all you have to really show, is that if you can find one entry that doesn't work, then you can't say it's a thing. So let's see. That's the same one they'd used. I guess it's just because it was in my brain, but I didn't remember it. So it's not closed under addition, so it's not a subspace. Okay. Now, sometimes finding that one example is really easy, and sometimes you just bang your head against the wall over and over trying to find one that disproves it. Okay. Moving on to example 4. And I'm going to have to take a very quick break here and turn up the heat because my hands are getting cold. In the early morning, I get sun in this window, but then as the day moves on, I get absolutely no sun because I'm on the northeast corner, and once the eastern sun's gone, I get none. So hold on just a moment. I'm going to pause the recording and let me run up and turn up the thermostat at least 1 degree. Hold on. Or the nurse said, if I get a fever, I go to the emergency room. I mean, with the anemia I've got and the low everything else that I've got, they said, no, don't risk it. Go straight to the emergency room. I don't want to go there. Okay, so let's move on to example 4. Okay, so I think I'll clear this. Any questions on 3 before I erase it? I am looking, well, I've got the, okay, sometimes it just doesn't, there it is. Sometimes this pad doesn't work if I have the pen anywhere close to the other pad. So let me clear that. All right, now I'll pick up and go from there. Here's example 4. Show that W, I'm so sorry. I'm cold, but I'm also running out of steam here. I'm not sure that'll help much, but so here's what W is. It's the set of all ordered pairs x1, x2, such that x1 is greater than or equal to 0 and x2 is greater than or equal to 0. Okay. With standard operations, show that it is not a subspace. SS stands for subspace of R2. Now R2 would be the set of all ordered pairs x1, x2. Okay? Now, it says show this is not a subspace of R2. Now, and again, anytime you're trying to show not, all you have to do is come up with one example that won't work. And if you can come up with one example that won't work, then you got it. Okay? And here is my proposal for an example. Give me a number, any number in the world, but make it positive, greater than 0. Give me a number. Any one. How about 3? And another number? How about 7? Just pick two numbers, any numbers. This is obviously in W. Ordered pair 3, 7. 3 is greater than or equal to 0. 7 is greater than or equal to 0. Okay? Now, that's in W. Now, remember what scalar multiplication is? If you multiply this by any real number, how about minus 1? That's a real number, isn't it? Minus 4/3 pi would work just as well, but I just chose an easy one, minus 1. Well, what would that give you? That would give you minus 3, minus 7. Guess what? This is not an element of W. Okay? Because W was only this. And remember, the two things you have to show, only two things you have to show, is that the addition of your components has to be closed, and this would certainly work. The addition of those would certainly work. 3, 7 plus 4, 18, that would still be positive numbers. But the other condition is that scalar multiplication would work. And remember, we can't limit or make exception to what value C, any C. You put a negative C in there, you're going to get a negative components of your ordered pairs, not going to be in the subspace, okay, or in the space, okay. So, yeah, they chose 1, 1, multiplied it by minus 1, got minus 1, 1, minus 1, not in the subspace, okay. Now, the next thing is going to lead to what we call nested subspaces, which is an interesting kind of a term there. I always think, I don't know if you've ever seen those Russian, I can't remember what they call them. They're almost like eggs that they're little figures that are fit inside other figures, fit inside other figures, fit inside other figures, and it keeps going up like that. And this is what we mean by nesting. One always fits inside the other one. You will often encounter sequences of nested subspaces. For example, consider the vector spaces P0, P1, P2, P3, all the way up to P sub n, where P sub k, any one of those, is a set of all polynomials of degree less than or equal to k. Remember how we did that. When they're less than or equal to, those are spaces, okay? So the set of all polynomials degree 0 or less, well, that would only be degree 0, so those would be constants, okay? All constant, in other words, all real numbers. And those all real numbers, P0, is a subset of P1, which is all polynomials of degree 1 or less. Well, P0 is to say all the polynomials degrees less than 1. you just have added that, so that's a subspace, a subset. P2 would be all polynomials of degree 2 or less. Well, 1 and 0 are both less than 2, so that would be a subset of that, and this would be a subset of P3. That's all polynomials of degree 3 or less. These are all less. This would include 3. And then you just keep up, not yuck. Okay. And you keep on going till you get less than P sub n. Okay? I can't tell if that's my phone or not. I don't know what that noise is. Okay, let me make sure nobody's out there waiting. Nope, just the two of us still. Let me just check. Yep. Okay, Kira, they've deserted you, it looks like. Okay. And anytime J is less than or equal to K, then you're guaranteed that P sub J is a subspace of P sub K. Okay? Now, if they were equal, that would be one of those trivial subspaces, the very space itself. But anytime it's less than, it works. It's a proper subset. Okay. Here comes example 5. This is a set of nested functions. Okay. Finally was beginning to get warm and now the heat shut off. So let's see if I can make it. What have we got? Another 30 minutes. Is that right? Yeah, 12:45. You would think this far into the term I'd have all these times right, but I don't. Okay. Okay, here's what we got. Let W5 be the vector space. VS is vector space, not versus. Of all functions defined on 0 to 1. This is so painful getting this to write and not mess up. Okay? And let W1 W2 W3 and W4 be defined this way. W1, set of all polynomial functions. Goodness, I'm so hungry I can hardly stand it. Defined on 0 to 1. All right, so let's just get straight here. All right, I'm sorry, I'm going to have to. I think I'm almost out of soda here. I am. I've got to get something because I'm actually feeling pretty lightheaded. Sorry about chewing. Okay. Okay. Now, W5 is a set of all functions that are fine on the interval from 0 to 1. Okay? That means your function has to be a function on that interval, defined on that interval. You're able to do it on the interval 0 to 1. W1 is a set of all polynomial functions defined on W1. Okay, I forgot to close off both of my braces here. Okay. Now, polynomial functions are certainly functions. So this is a subset of that. Okay, W2 is a set of all functions that are differentiable on 0 to 1. Now, certainly all polynomial functions are differentiable everywhere, so they're differentiable on 0 to 1. This is a set of all functions that are differentiable. Well, there are other functions other than polynomial functions that are differentiable on 0 to 1, so W1 is a subset of W2, but W2 is still a subset of W5, and that's because all functions defined on 0, 1, even functions that aren't differentiable there, but the ones who are, they're defined there. Okay, so what's W3? W3 is a set of all functions that are continuous on 0 to 1. All functions continuous on 0 to 1. Okay, now certainly functions that are continuous could have points, cusps, and things like this that wouldn't be differentiable. But they're still functions defined on 0 to 1, so W3 is a subset of W5, but W2 is a subset of W3, because differentiable functions are defined first there, but they're all differentiable functions have to be continuous, but not all continuous functions have to be differentiable. Well, then what's our fourth one? W4 is a set of all functions that are integrable on 0 to 1. Okay. Goodness gracious. I'm about okay. Now, so trying to think of some examples or counterexamples here. W3, they have to be continuous. Now, all continuous functions are integrable. but not really all integrable functions have to be continuous. Okay, now that's kind of a stretch, but it certainly is true. I mean, you can integrate in a piecewise fashion functions that are not continuous. Okay, and you can't differentiate them, but you can integrate them. And then all functions, certainly integrable functions, would be in all functions, but not all functions are integrable. So here we have a situation, and it says show that, and I've just talked my way through it, but it says show that W1 is a subset of W2 is a subset of W3 is a subset of W4, and that's a subset of W5. Okay. And that's the first part of it. And that WI, I believe that's what that subscript is a subspace of, remember SS is subspace of WJ for any time that I is less than or equal to J. Okay. And I think I've already done this as I was giving the thing. As I said, that all polynomial functions are differentiable, but not all differentiable functions are polynomials. All differentiable functions have to be continuous, but not all continuous functions are differentiable. I gave the examples there. All continuous functions are certainly integrable, but not all integrable functions are continuous. That's harder for me to give a counterexample to. And certainly all integrable functions are functions, okay, but not all functions are integrable. Okay, so I think we already did that as we were going. Okay, now let's get down to leading into theorem 4.6. So okay, hold on just a moment. I've got to do something else, or I'm afraid I'm going to. Sorry to be eating in class, but I was getting awfully weak feeling there. Okay. I'm hoping it's the anemia and not something else. I know I've got that. Now, as implied in that last example, if U, V, and W, they're capitalized, so we assume these are spaces of some nature, or at least sets, okay, of some nature. But now they're saying they are vector spaces. Vector spaces. Okay, such that W is a subspace of V, and V is a subspace of U. Now, if that's the case, that was supposed to be an if there, for some reason it disappeared, then W must also be a subspace of U. Okay? Now, what that's saying is, it's that whole nested concept here. If W is a subspace of V, everything that is required of W has to, every element in W would place it in that subspace of V. Scalar multiplication, vector addition, everything must work properly. Okay? Now, if V then is a subspace of U, and that means all the things must work for every element in V as well. Well, all the elements in W are elements in V, so therefore, and they're all in the subspaces, so they've got to be, W has to be a subspace of V, of W, I'm sorry, of U. All right. That's what this next theorem shows, and I think I'm going to type this except for one thing, and I'll write that in. Okay, so I think I'll go to the typing mode here. If, let me get my text box done. If V and W are both subspaces of a vector space, that came out wrong. Oh, that came out right. Of a vector space U, then the intersection of V and W now, here's the part I've got to write in. Denoted by V W is also a subspace of U. Okay, let me drag this out. All right. Now, let me, whoa, before I do that, all right, let me draw this in, and I think I'm going to draw it in baby blue here. Not quite baby blue, but some sort of blue. Now, for some reason, my screen sharing paused. I don't know why this kind of stuff happens. Okay, there we're back again. A intersection is this, yuck, it's such a pain. What did that happen? Yuck. Okay. Now, this is the symbol for intersection. V intersect W. That's all I was trying to do, and then all these other things happen. Okay? That's also a subspace of U. Yuck. Need to get... Well, I can't go back to my text, so I thought I had the period in there, but it didn't show up, so I'll write it in. Okay. If V and W are both subspaces of vector U, and then the intersection of V and W, if there is an intersection that's denoted by V intersect W, is also a subspace of U. Now, they show this with a Venn diagram, or something that looks like a Venn diagram, and I'll try to do it here. Now, I like to make my universal set as a rectangle. They used a circle, but I'm going to use a rectangle. That's my universal set U. This one. Okay, the big space. And here is space V. Here, and these are both subspaces. They're all contained within here. Now, subsets would be contained too, but this is the subspace, okay? That everything in V is a subspace of U, everything in W is a subspace of U. So what's in here, of course, is it's in V and in W, and so all these things have to be subspaces of U as well. This is what V intersect W is, the space that is shared by both. Okay. Now, this doesn't prove it, it's just sort of an illustration of it. But if you were to choose an element in V that was also in W, it would be in V, V1, V2, you know, everything there must add to be in V. And if they also happen to be in U or in W, well, look at it. They're both inside U. So there's just no way they wouldn't be able to operate that way, because they are in V, and V, you know, is a subspace. Okay. They told you that, and W was a subspace, so therefore of U, so therefore anything that fits V and W has to fit in U as well, U as well. So I don't know. Those are the kind that seem so incredibly patently obvious. You wondered why in the world they either bother to show them, but I guess there is a reason for it. So let's move on to how we're doing on time. Yeah, we got plenty. Let's clear those drawings and go to the top of page 171. Subspaces of Rn. Okay. Now, Rn is a convenient source for examples for vector spaces. So the remainder of this section is devoted to looking at the subspaces of Rn. All right. So example 6. Determine whether each subset is a subspace of R2. Okay. Here's the A part. I sort of want to go back to my black, I think. Okay. Here's the A part. The set of all points on the line such that x plus 2y is equal to 0. Okay. That's certainly a subset of R2. You got ordered pair, x, y. Okay? Now, is that a subspace of R2? Okay? Now, the first is that if you had in here one of these, x1 plus 2y1, the x1, y1 was one of those, that has to equal 0. And another point in there, x2 in here plus 2y2, that's also equal to 0. Okay? Well, sure enough, if you added those together, you'd have x1 plus x2, that's a number, okay, plus 2 times y1 plus y2, add those together, add these together, you equal 0. Okay, so under vector, or vector addition, that works. That this number here, that's a number in there, plus twice the number in there, it's got to equal 0. So that works. Well, the scalar addition works. Okay, how about scalar multiplication, vector addition works. How about scalar multiplication? We could use 2. I'd rather use c times x1 plus 2y2 at y1. That's a 1 there. That's ugly though, isn't it? Well, the thing I wanted to erase was the one thing that wasn't going to erase. This would be cx1 plus 2c y1, okay? The question is that equal to 0? Well, c times 0 is 0, okay? And so actually you go the other way and do that. So scalar multiplication works. So yes, that one works. That is a subspace. That line in that plane works. Now, the B part said the set of all xy ordered pairs such that x plus 2y is equal to 1, is that a subspace of R2? All ordered pairs. It's certainly a subset, okay? But let's do our scalar. It doesn't matter which one. Vector addition, if you do x1 plus 2y1 is equal to 1, that certainly would be in there, and x2 plus 2y2 equal 1, that would certainly be in there. You add these together, you have x1 plus x2 plus 2 times x1 plus y1 plus y2. that now is equal to 2, that would not be in it. That the sum of these two, that would not equal 1. That is not equal to 1. Now that's really the harder one to do. The easier one would be multiply it by C, and as long as C is not equal to 1, for any other C in the world, C times X1, Y1 would not fit the bill, because it would be C X1 plus 2C Y1 would not be equal to 1, because you could factor out the C, and if that's not 1, that would multiply both sides, including the 1. That would become C then, and C is not equal to 1. Now that still is not the easiest way to prove this, that it doesn't work. The easiest way to prove it is to see, remember, the 0 vector must be included. 0 vector up here works perfectly. 0 plus 2 times 0 is equal to 0. So the 0 vector does work. Down here, it doesn't work. 0 plus 2 times 0 is not equal to 1. So 0 would not fit that bill. It would be equal to 0. Okay. All right. So several ways you could do that. Set is non-empty. Fine. Closed under addition. I don't think so. It is not, however, closed under scalar multiplication. Wait a minute. I'm looking at the wrong problem. Sorry. Okay. The first one, solving for a point there, you see that goodness, they go a very difficult way to solve this one. It says solving for x in R2, you see the x is equal to minus 2y, and if you let y equal t, that'd be minus 2tt, where t is any real number. Show that is closed under addition. Boy, do they ever do a difficult way of doing that. And they just went, for the B one, they went straight to the 0 vector thing. Okay. Now, 3 minutes. Do we have 3 minutes to do 171? No, the middle of 171. Let's see it. Okay. Now, let me clear this. Of the two lines in example 6, okay, the one that is a subspace is one that passes through the origin. That is characteristic of the subspaces, and let me just show you that. I don't know if you have a book that you can look at, but there was the one that goes through the origin was the A part, the one that went above that was the B part. Okay, one that went through the origin was a subspace. The one that did not go through the origin is not a subspace because it doesn't have the 0 vector on it. Okay, that would be the origin. Okay, so if W is a subset of R2, then it is a subspace if and only if it has one of the forms listed below. Okay? And here's what they are. One of these, okay? W is a single point 0, 0. That's that trivial case. Remember, we talked about that earlier, okay? So that certainly is. W consists of all points on a line. Now this is an R2 only, okay? On a line that passes through the origin. Yuck. Okay. 3. And that's the one we just showed. W consists of all sorry, R2. So remember, these are our two trivial cases, the 0 only and everything. Other than that, in R2, two-dimensional space, then it has to be any line that passes through the origin. Any line that passes through the origin. Okay? That's it. Now, and I think yes, we have run out of time. So let me make a quick adjustment here to my mark, and we will begin next time. Can't remember what, oh, there's my pencil. Okay, with the 3 conditions graphically. All right, and we'll pick up and go from there. Let's see what homework exercises you can do based on what we did. We came close to finishing 4-3. Okay, I think you can do any of the odds 1 through 5. They all should be at Calc Chat. I think you can do any of the odds 7 through 19. They should all be at Calc Chat. Okay, I think you can do any of the odds 21 to 27. They should be at Calc Chat. 29 to 35. They should be at Calc Chat. Hold off and we'll stop there and pick up with those that deal with R3 after we finish next time. Okay? Any questions? All right. Then I'm going to stop sharing if there are no questions. And my first 2 classes today, I had one student in each class that said, I need to ask you a question at the end of the thing, but I need everybody else to leave. So we had to do that and wait till everybody else got out of the class, and then those students, well, we couldn't get everybody out of the class in the first one. Some people had just left their computer running or the phone running or whatever, and had gone off and done other things, didn't realize we had finished class. So since she couldn't get it out, she said she would try to email me the things she said she had tried before, but email wouldn't go through. I don't know what that was about. So she just backed off and didn't ask. The second one, 2 people still hadn't disappeared, so she went on and asked, and we got that taken care of. Well, you are in the perfect case that you were the only one in the room. You could have asked a question, but of course you didn't have a question. I assume you don't. So anyway, first 2 classes were identical, and that was bizarre. This one, however, is not. Good. We'll see you we'll see you tomorrow, okay? Twice, and then once on Thursday, and we'll wrap things up for the term. Take care. Bye-bye.